Uh, can you give me, tell me what it is?
Yeah, sure. So for 5.4, it says suppose a 2 gigahertz radar antenna of effective area 6 meters squared.
F equals 2 gigahertz. This is 5.4.
This is 5.4 at the center.
And go ahead.
So its effective area 6 meters squared and transmits at 100 kilowatts. It's a target with a 12 meter squared radar cross section.
It's 12 kilowatts, did you say?
Transmits 100 kilowatts.
Oh, I'm sorry, 100 kilowatts. Go ahead.
If a target with a 12 meter squared radar cross section is 100 kilometers squared.
All right, so sigma here is how big again?
12 meters squared.
Oh, this is 12 meters squared. All right, and it's 100 kilometers away?
Yes, sir.
Uh-huh.
And then as for the round trip travel time, the received power, and the maximum detectable range. Yeah,
And
the
P.
maximum detectable power is 2 gigawatts.
So P min is 2 picowatts. This is really just a straightforward problem. There's not much here, but we'll go through it. When I'm doing this, first we'll get the round trip travel time, the delta T. Well, you know the actual signal goes 2R. Do you all see me on this one, class? So it's going to be 2R divided by the speed of light. That's as simple as it gets. The velocity is the speed of light. 2R is the distance. So this is going to be, that's going to be 2 times 10 to the 8th over 3 times 10 to the 8th, or 2/3 of a second. I don't know what's in Wentworth's book, but that should be it. Is that it? Is that 100 kilometers? Or
Yeah, it's 100 kilometers.
well, 100 km is 10 to, oh, sorry, km. By God, I'm sorry. I'm thinking this is, if it's 100 km, this is 10 to the 6. I'm sorry about that. So this is going to be 2/3 times 10 to the minus 6. Is that right? Or me minus, sorry, minus 2. My bad.
The answer is 2/3 of a millisecond.
All right. Oh, wait a second. It's 100 kilometers, right? So if it's 100 kilometers, that's 10 to the 5th here, sorry. So over 10 to the 8th, which is 10 to the minus 3rd. I'm sorry. You're right, 2/3 of a millisecond. I'll wake up. Go ahead. Now that's the round trip travel time, but that's a straightforward calculation. Just the distance traveled divided by the velocity. I'm sorry about that. The next is they want the received power density for this particular problem. So P received, you can get a lot of ways. I'll do it. I'll just go through this. One thing is that I know the formula, the simplest formula if you want to get it all into one, right? Where you get just gain, would be gain a transmitter, gain a receiver, times sigma times lambda squared. That's on top. And then 4 pi cubed here, r to the 4th. That's one equation that takes care of everything. Takes care of the incident power density on the target, the amount of energy scattered, the 1 over r is falling off as the power is scattered back to the source, to the actual transmitter, and that's what it will be. Here, the receiver and the transmitter have the same effective area. So that means gain a transmitter is gain a receiver. And if you remember this, that the effective area is lambda squared over 4 pi times gain in general of the system. So therefore, gain is equal to 4 pi over lambda squared, right, times the area. Do you all follow me on that? Well, didn't he say the transmitter and receiver are the same, or am I wrong?
It's 6 and 12.
I'm sorry about this, and I didn't hear it right. Is this the area of the transmitter?
Yes.
And what is the area?
It's over there on the right. It's 12 meters squared.
Isn't that the radar cross section?
Yeah.
Yeah, I think they're the same. Transmitter and receiver have the same area, and that's the size of the target. So if we do this, you can see that I can replace the two gains with this equation. Therefore, I have P received here equal to gain a transmitter, and you can just put it down, 4 pi over lambda squared times gain, and I'm just going to leave it gain, and then you're going to take this a second time, so now I'm going to get 4 pi over lambda squared squared times gain squared of the transmitter times sigma times lambda squared over 4 pi cubed, and then it's r to the fourth. Now, I'm going to stop there for a second. Most of you see that things start canceling if we look closely, if you want to cancel. Do you all follow me on this? Remember, the gain is 4 pi over lambda squared AE, right? So in here, I have 4 pi over lambda squared, right? And then I have gain squared. Do you all follow me on this? Because you're multiplying this twice. Do you follow me? It's gain of transmitter, gain receiver, right? They're the same. So it's just this squared, gain squared, if you will, right? And gain is 4 pi over lambda squared times the aperture or area. Correct? Is everybody saying this? You're looking at me. I have the gain squared, don't I? No, isn't that right? First gain times second gain, gain squared.
Yes.
But what?
I think that gain transmitter should be area.
Wait a second. Oh, I'm sorry. I'm sorry. Yeah. You're absolutely right. It's been one of them days today. This should be, let me just put it the way I should say it. It's going to be, since this area is given, I should just put quantity 4 pi lambda squared times the effective area. I'm very sorry about that, squared, times sigma times lambda squared. There. I apologize for that. You all see what I'm doing here? I'm just trying to take the what it's defined as up here and put it in there. Now, with that, you can cancel some stuff if you want, but you don't have to. The thing we really need is lambda, and since the frequency is given here as 2 gigahertz, lambda would be equal to C over F, or 3 times 10 to the 8th divided by 2 times 10 to the 9th, right? Well, that's going to be 3 halves times 10 to the minus 1, or 0.15 would be lambda. And if you want, you can cancel some of these things. I'm going to leave it like this for now because you can just plug in the numbers and give me the answer. All right? What do you get for the final answer in this? 1.5 picowatts times 10 to the minus 12 watts. Is that consistent with what he has? Don't always assume his answer is right. If that's right, then what next? What else they want? The minimum, right? The range for the minimum detectable. All right, now here they say the minimum is 2 picowatts, and I'm under that, right? So I'm too far away. Do you follow me, class? This is one of those things, all we're going to do is solve the problem inversely. We're solving for R, right here. So if I take this equation, actually, I'm going to modify this. I have 4 pi squared up top, 4 pi cubed here. I'm going to leave the 4 pi there and get rid of that one. Then I have lambda to the fourth here times lambda squared, so I'm just going to bring a lambda squared downstairs. Aperture squared, sigma r to the fourth. That should work. Do you agree with me as far as the equation? This is an equation with just aperture for P received. Do you all agree with that, class? I'm just trying, the only thing I'm trying to do is reduce the number of, I guess, steps, mathematical steps. So I've got area squared sigma over 4 pi, lambda squared over r to the fourth, right? I'm solving for r. Do you all see this, class? This is not a hard thing to see. I've got an equation with r as the only unknown because this is given. So now I simply take that r to the fourth here would be equal to P received, right? And that would be minimum P received. Or I'm sorry, r to the fourth comes up here, and then I have the effective aperture squared times sigma over, and this is going to be 4 pi, and then it's going to be lambda squared. Now that's r to the fourth, so I have to, yeah. We're solving for what? This is the P received, isn't it? I mean, boy. let me do it this way. When we started doing this stuff, I didn't. Didn't I put P transmitter here? Oh gosh. Let me. That should be the equation. It should have P transmitter there. Huh? I did put it there or not? I didn't. It should have P transmitter there. I'm sorry about that, but I'm gonna go through this again. Our transmitted power was 100 kW. Let me just make sure that this is one of those days that I'm going to start again. I'm going to say P received in general. Then we'll go from here. This P received, pardon me, is equal to P transmitter, right? Then I usually say it's over 4 pi. Then you can cube this, r to the 4th. Then it's going to be times gain of transmitter, gain of receiver, sigma times lambda squared. That's the ingredients of this equation. We can go through it step by step and how to get it. The only thing I'm going to do is replace the gains, the two gains, by 4 pi over lambda squared times the aperture. So up here, if I put 4 pi over lambda squared times the aperture, and then I have to square that, now I have a single equation for received power in terms of transmitted power. Sorry for the mess up. You all with me on this, class? Now, if I have that, if I know what P received is, and I know what P transmitted is, I can just do a ratioing here. Y'all agree with that? And then what I'm going to do is simplify it a little. I got 4 pi squared, 4 pi cubed. Leave it as just 4 pi there. I have lambda squared squared, or lambda to the 4th, lambda squared. So I take a lambda outside of that. This is still squared. A lambda squared outside. And now it's effective aperture squared times sigma. So this should be the aperture squared times sigma right there. Now they give us this ratio, and we're going to solve for r to the 4th. So what I'm going to do is take r to the 4th on this side and say it's equal to the aperture squared sigma over 4 pi lambda squared. And then when I divide by this, or multiply by the inverse of it, now I multiply this side by the transmitted power over the received power, or the minimum received power. And that would be r to the 4th. I'm just manipulating one equation. So I'll take the 4th root over here. And that should do it. So what is that? 93.5 kilometers. Okay. And this isn't a tricky problem at all. It's just manipulation of a couple equations. What else did they ask?
That was it.
All right. Do you have another question? I gave you some problems that aren't in the book too, right? Mm-hmm. Which one is it? Yeah.
We weren't assigned 57, but if we do it.
Okay. I'll be happy to do that, but I want to just do the ones that I gave you first, okay? What? I didn't give you an answer? No problem. Why don't we start with the second one, since I didn't give you the answer. One sec. Let me drink a little more of this coffee. Gotta wake up from a big lunch. Okay. Give me the second one problem, the one I didn't give you the answer to. What does it say?
A plane having RCS equal to 10 meters squared is flying 500 meters per second.
10 meters squared. It's flying 500 meters per second.
It's flying at 30 degrees in a radius vector from the radar.
30 degrees. Uh-huh.
The 10 kilowatt radar has a frequency of 9.4 gigahertz. The gain of transmitted is 30 dB. Gain of receiver is 20 dB.
30 in a dB. Gain of receiver is 20 dB. Go ahead.
Oscillates with a
a PRI
Yeah,
equal to, say it again.
2.4 milliseconds.
Uh-huh.
With a 20% duty cycle. And the
All
plant
right, that's tau over T equals 0.2. Go ahead.
the plant is 10 kilometers away.
Okay, so that means R is 10 kilometers away.
And it wants the power received and the Doppler frequency.
P received and F Doppler. All right, this is the one that it's just to make sure you can think through it. So the problem it's yeah.
You didn't write it down, but it's a 10 kilowatt radar.
Power transmitted is 10 kW, 10 kilowatt. All right, with this problem, for the first part, it's an absolutely straight just plug and chug thing here. Now, a gain of 30 dB is 1,000 or 10 to the third. A gain of 20 dB is 10 squared in terms of the linear values. Just make sure you don't make the mistake that people just stick in 30 or 20 a lot of times. So those are in dB. This is linear, right? The linear gain. The next thing I've got to do is, if I want P received, I can go to the straight radar range equation, and I can just take transmitted power, gain a transmitter, gain a receiver, lambda squared, sigma, and then over 4 pi cubed, r to the fourth. We can just do that straight away, and if you punch the numbers on this one, the one thing we need is lambda. Lambda for this one would be equal to C over F, or 3 times 10 to the 8th over 9 times 10 to the 9th, so whatever that is, 0.02 something. I don't know exactly, 29, 28, something like that. It doesn't really matter. But if you take that and plug it in there, you should be able to get this number very effectively. By the way, I know today I've been sloppy, and I apologize for it. I am beat, but that coffee should get me. But when you're doing this, I'm going to warn you on a test. And in general, if I do this stuff, like if I'm doing a formal design, I run these equations at least twice. All right, I write them down and go through them, work through them myself to make sure there's no mistake twice. I mean, admittedly, I'll use Mathcat or MATLAB to do this stuff, but I'll make absolutely certain everything's dialed in right. I get a little paranoid right here because it gets too easy to make mistakes at this point. Your focus isn't here. When you punch that in, what do you get for this power received?
I got 513 milliwatts.
513 milliwatts. Anybody confirm that? If you have your calculators, or if you are using Mathcat, and I'm encouraging that, or whatever you use, what do you use? Python? If you use Python, whatever you use, I mean, I like to set up systems of equation, just change variables. I don't like to have to keep on punching in equations like this radar range equation over and over again. It doesn't help me.
I got 0.513 picowatts.
Picowatts. So we got milli to pico.
Yeah. I got pico as well.
I'm going to bet it is pico, but I don't know. Could you run the numbers one more time? Remember, transmitted power right here is 10 to the fourth watts, not 10 watts, 10 to the fourth. Gain of transmitter, 10 to the third. Gain of receiver, 10 squared. Lambda squared sigma over 4 pi, but it's r to the fourth, and r in this one was 10k, so that's r. 10 to the fourth to the fourth is 10 to the 16th, which is a big number. But what do you guys get? Run them again, make sure it's right. Okay, 512 pico? Is that what you get now? I think I'm going to go with 512 picowatts. 0.513 picowatts. Okay, I'll trust you on this. It's easy to make a mistake here, especially because you've got orders of magnitude. First, you've got to make sure you're out of dB into linear, so it's 10 to the third, 10 to the fourth. Then you've got to make sure you've got the proper, because I was messing this up earlier. That's 10K, that's 10 to the fourth. 10 times 10 to the third. Now the Doppler shift, this is the one thing I wanted to get you thinking. Doppler shift in general boils down to really 2 times the velocity over the wavelength, right? That's the simple equation. I want you to listen to this. It's not in your book, but you should have. Sorry. this is what it is if this plane's flying directly at this. Do y'all follow me? Please listen. If the plane is flying right at the radar, that would be the Doppler shift, 2 times the velocity divided by lambda. But you need to take the projection of the velocity of the plane in the direction of the radius vector. Can you all see that's be the cosine of 30 degrees would come in here? So this is really going to be times cosine of 30 degrees. It's really the cosine of the velocity vector and the r vector. In some cases, you'll see a dot product used there. You'll see r vector, and then there'll be a dot where you're going to have, on top, you'll have ar dot v to get it. But you don't have to worry about that. It's the cosine of the angle between them. And what do you get for this? Well, this is equal to 2, and the velocity was 500, right? 500 divided by lambda, and lambda, whatever that is, it's 9.4, by the way, here. What do you get for this, guys?
I got 27.1 kilohertz.
Anybody else?
I got that.
All right. But I just wanted you to think about that. Yes, sir.
So in the problem you gave us PRI sub T and 20% duty cycle, we use them. When would we?
Well, in the next part of this problem, were they referenced in the next part or not?
No, there's nothing.
All right, good question. This right here details what the actual transmitted pulse in time looks like. So it says, if we look in time, and this is what I was getting at last time, what I'm going to have is something with a 20% duty cycle that would look like this. And this is the envelope of what's called a baseband. Yeah.
PRI is full period. Right then.
PRI is T, yeah. This is equal to T. That's actually, it's the length of one pulse. But only 20% of the time is it up, 0.2. So now this is equal to the PRI or T, and that is 2.4 milliseconds, which means this is 0.2 times 2.4 milliseconds. That's all it means. Now remember, this is just an envelope of what's being transmitted, right? And the actual power is on there, it's off, it's on there. I'm going to tell you a few other things with this. What we're talking about with the radar range equation here, right there, that power is usually the average power over a cycle, not the peak power, all right? It's the average power. And if you think about that, average power in a waveform would be equal to tau over T times, which we call would be the peak power. So during this part of the actual transmission, that's when all the peak power is being transmitted, right? Then it goes to 0. So this is the average power during that period. Y'all follow me on this, class? Now that's usually what's done. He doesn't break it down this way in Dr. Wentworth's book. So just something to keep your eye on. Now, why would this stuff be of importance, or what questions could come out of it? Here's some of the questions. The first could be, what was the maximum non-ambiguous range? Remember we talked about ambiguous range? This is the maximum unambiguous range. Do you remember how I told you to calculate that? You're always, that's right, you're always going to take the total distance traveled, right? But we actually traveled 2r, right? Because it goes out and back, right? We say that's equal to T times C. So if we divide this by 2, this will be the maximum non-ambiguous range, and it'll be in kilometers usually. Then there's something I call the range resolution, delta R. And delta R has the same exact formula, except instead of T, you use tau. And this becomes C tau over 2. And what this gives you, the second one gives you the minimal distance you can distinguish two different targets. Targets are closer than that, and it's in the radial direction. You can't distinguish them. Do you follow me on this, class? So if you got two targets and they're close to each other, if they are at a distance delta R or less, You can't tell if there's 1 or 2 or 3 or 4 or how many. And that's one of the reasons you fly in formation. You cloak your numbers. This tells you the range, how far out you can see clearly, you might say. Anything out to that range is something that's going to be, when it gives a return, it's non-ambiguous. All right? Usually the way they do this is by the time you get to the non-ambiguous range, anything reflected back from any targets you expect will be in the noise and you won't be able to see it anyway. That's the way they design these things. At least it's part of the design process. So that would be for that one. This would be maximum range, or I mean, not unambiguous range, and the range resolution. Does that make sense?
Is tau always 2 over 2?
Tau, no, well, tau here is going to be what? It would be 0.2 times t, right? Because this is 20% duty cycle. It can be 0.5. It's used sometimes. It can be down to 0.01 for things that are trying to get real clear resolutions. Anybody have a fish finder in here or anything? You go fishing? You ever hear of chirp mode? All right, now I don't have time to get into this, but in radar, what chirp mode is this, is they sweep the signal during this on time. They start at an F0 and they sweep it up to some F0 plus an actual sweep, an FS through here. And so it might start at 9 gigahertz, go up to 12 gigahertz just in this small period of time when it sweeps over less than, say, 5 milliseconds. What that does is, when you look at the spectral domain, what happens is you get a very sharp resolution. You'll be able to much more clearly define distances. Anybody who used this, have you noticed how your branches or anything like that underwater are very clear? But the return, the strength isn't much because you do, that's the trade-off. You lose the actual power compared to your regular sonar. I'll talk about some of this later if I get through my coursework. I'd love to talk more about radar because there's so much more to this. And frankly, it's fascinating, especially with what you can get out of a radar signal if it's done right. I'll tell you one other thing, too. We always, as engineers, try to do what nature does. I don't know if you realize this. Our very best sensors that we have, electrical sensors we built, can't come near a dog's nose for detecting particles. Dogs' noses can detect 1 in 10 to the 13, 10 to the 14 particles. We get down to maybe 1 in 9, 10 to the 9. As good as we are, with bats, a bat doesn't use electromagnetic radiation, but it uses echolocation. It's similar to sonar. Bats have the ability, with just 1 mouth and 2 ears, to locate anything, texture, everything in pitch darkness. They can identify a moth. They can differentiate a moth from a bee, from anything like that. So, and by the way, they're not putting out a lot of power. So we try to replicate that with radar, with electromagnetic radar. Now, to do what the bat does in the electromagnetic world is so far out of the realm of possibility, we don't even try to go there. What we try to do is do little bits and pieces in the right direction. We're just trying to get a radar can be adaptive over a small band of frequencies to possible targets and minimize noise. It's still a mess, but what I'm learning, I'm trying to tell you about this, is if you're an engineer and you're trying to do something, look at nature and see if it's got something dual to it, and then study it. Does anybody know that an owl, when it flies, is noiseless, basically? Anybody in here? Who knows that? I'm curious. All right. Well, you know how long we've been trying to develop helicopters and stuff that are silent? Any idea? You know what they're doing now? They're looking at the owl. And they're actually making a lot of progress. It's all classified now, I'm sure. And what I'm telling you is probably going to get me in a little trouble if somebody hears it. But it doesn't matter. They always look at nature. Please look at nature if you want to find out. If it's something, you know, that parallels nature, you're not going to outdo them. I don't think. That's my little blurb on how you do good engineering. Take a look at the natural world and see what's out there. There's a lot of stuff right now with adaptive stuff based on artificial intelligence to adapt to the environment quickly, and it's not easy to do that, by the way. You know, these Google cars and all that? Last thing on this. Now, you guys are really on the cutting edge of getting to something where quantum computing could be of interest. I'm not sure if it's going to happen, will autonomous vehicles with artificial intelligence, with all the necessary things, the radars and everything like that are adaptive or coming into view, super lightweight, not just a radar, but something that has a broadcast signal in it so you can communicate with just one transmitter. Things that go all digital means you eliminate the need for mixers, for big components, inductors, capacitors, and all sorts of amplifying stages. It'll go all digital. It's like software-defined radio. This is the push. The thing that limits it is speed right now of our processors and the actual power of processors. And frankly, the weight in some cases. But that's where you're going right now. People in this room would be working on this. If I were you, I would encourage you to go out there and take a look at some of the latest, greatest technologies that are coming out there in some of these magazines, and then read about one, get interested, and it'll change the way you think about doing homework. Trust me, it really helped me when I was in school. Did you want me to do another one?
57, please.
What is 57?
Times at 10 kilohertz gigahertz radar antenna.
10 gigahertz?
10 gigahertz.
Mm-hmm.
Effective area 100 meters squared to be used to determine the distance to the moon.
100 meters squared. All right.
The moon radius 1.74 times 10 to the 6 meters.
Range is equal to what?
The radius of the moon.
Range to the moon, not radius of the moon.
Yeah.
It's just the radius.
Right. All right. Radius of the moon. Okay. Our moon equals what?
1.74 times 10 to the 6 meters.
Okay.
As a measured radar cross section.
All right.
6.64 times 10 to the 11.
Meters squared. Go ahead.
The 27 picowatt echo system signal.
He received is equal to 27 picowatt. Uh-huh.
That's received after transmission in 2.56 seconds.
So the round trip time is 2.56 seconds. So delta T is equal to 2.56 seconds, 2.56 seconds. And they want the distance to the 2.56, is that right?
2.56 seconds.
All right. Well, we know that C times delta T is the distance, right? But because it had to go out there and back, it traveled twice as far, correct, class? So we divide this by 2, and now we get the distance to the moon, R to the moon distance. So that would be 3 times 10 to the 8th divided by 2 times 2.56. And what do you get for the distance to the moon? 93 million miles?
3.84 times 10 to the 8th.
Times 10 to the 8th meters, right? Turn that into miles. What is it? You can take that and I'm doing it the wrong way. I know it's 5,280 feet in a mile, but I'd have to, don't you have, you guys got Google? Just change 5.84 times 10 to the 8th meters to miles. I want you to know this number because it's something that you should have a perspective on as engineers. Anybody?
$238,606.
200 and what? 606 miles. I think the distance to the sun is 93 million miles. Check me on that. Distance to the sun. The reason I'm doing this is giving you perspective on relative distance. Huh? 93 million miles. Now, it takes 2 seconds to get a reflection back from the moon. Compared to the sun, I think it takes, I want to say, minutes for light to get from the sun to the earth, all right? Much greater orders of magnitude difference. It's important to realize scale in this one, because if you're doing anything with space, you got to realize just how small the earth is and how far we are from the sun. If you actually made, something to scale, you wouldn't believe how small we are. Most of the whole place is nothing. But you don't get that if you look at something like in one of these basic astronomy books. You get to thinking, oh, the Earth's big, the sun's just a lot bigger, and there's not a lot of distance. Incredible distances. All right. Any other questions? Yeah.
Just one last part.
All right, well, if you think about this, if we want P radiated, I'm going to go backwards fairly quick. So P received, we know, is equal to P transmitted, gain receiver, times sigma times lambda squared. You don't have to do this, but just watch. R to the fourth, right? So if we want transmitted power, the only thing we're going to do is multiply this by 1 over everything else. And we can say transmitted power is P received here, 4 pi cubed, R to the fourth, distance to the moon, over gain transmitter, gain receiver, sigma lambda squared. And that's it. You're doing a simple inverse problem. I don't know how much power is translated. You got the distance, you've got R, you've got the gains, or I should say the apertures, so you've got to change that. You can get the gain by simply saying the gain is equal to 4 pi over lambda squared times the actual aperture. And this is 100, so it's 4 pi over lambda squared can be the gain that you use in that formula. But you can do this, right? What did you get the... This should come out right. Aperture's 100. What? 10 to the 6. Is that right? Okay. It's just an inverse. Any other questions before I get going? All right. Now today we're starting to talk about EMC and EMI. It's the next chapter. This is one of the areas that I teach a course in this. There's a lot to this, and it's very, what it does is it takes what you believe to be true and it revises it to account for all the physical things involved that you have to be aware of. And it starts with wires. So start here, get a new page, and call this EMI, electromagnetic incompatibility or interference, or EMC. That's electromagnetic compatibility. Now, the goal is twofold when we do this. First, to understand if you have a system, how much is going to be radiated into the currents into the wall or radiated around you. And the second thing is to take a device and then prevent radiation from bothering it. All right? So it's either analyzing to see how much goes out or figuring out what you basically need to do to make it non-susceptible to radiation. It's both transmitting and receiving problems is what I'm getting at. So when we do this, we start with wires. Now please write this down. When we start with wires, we start with your standard copper wire. This wire has a certain radius A, it has a certain length L, right? If I was to hook up something like this and put a battery here with a voltage V, it would induce a current I on this. That battery indicates it's DC, and the current I would simply be V over the resistance of the wire. This wire is long and skinny. It's got a cross-sectional area of pi a squared. And it has a conductivity sigma. So this is a good conducting wire. Now, one thing that is not stated explicitly in Wentworth's books, but L is always assumed less than lambda over 10, where this whole thing falls apart. Then you're dealing with a different type of radiating element. Lambda over 5 maybe, but typically lambda over 10. For short wires, this analysis works. It doesn't work for long wires, and you have to be aware of this if you're an engineer. So when we look at this, we talk about something called the DC resistance, or RDC of this wire. Now the key to this thing is twofold. First, the cross-section of this wire does not change at all. Constant cross-section, and this is at DC. Well, RDC is always proportional to the length of the wire. Most of you know this, right? It's inversely proportional to the conductivity. The more conducting a wire is, the lower the resistance for a given length. And it's inversely proportional to the area, cross-sectional area. That means it's L over sigma pi a squared for a typical round wire. A is the radius of the wire. Most of the information you need about wires is in what's something called the American Wire Gauge, AWG. You can look it up online, and it'll dictate all the radiuses, all the conductivities, if there's anything. It'll basically say how many wires are bundled together and what the radiuses are of each wire, if it's a stranded wire, and you can get a lot of information there. Now that's DC, but when you have an AC or for high frequency, just put high frequency down. When you have high frequency, now the current hugs the surface. And the way we determine when we need to go to the second equation is you calculate the skin depth. This is the skin depth. The skin depth is 1 over the square root of pi f mu sigma. That's mu is mu relative times mu naught. Sigma is the sigma of the wire, the conductivity of the wire. How many remember the concept of skin depth? Y'all got it? All right, that skin depth will give you a value. And if the skin depth is less than or equal to the actual radius of the wire, then you default to R high frequency. And the R, I think Wentworth is high frequency. It could be AC, but for this one, what you end up doing is saying that now it'll be just like RDC. It'll be L over sigma, but now the area here is different. And here's how so. If you think of this wire's cross-section, right? When we have DC current flow, it flows uniformly, ideally, through that entire cross-section, right? But when we have AC current, what actually happens is AC current effectively only penetrates one skin depth. So if we look where the current is, it's all hugging this area here, right? Now this is a skin depth thick right there. And this is out to A, which means this effective radius is A minus delta. Follow me on this, class? Can you all see it in the back? It's going to be the full radius minus the skin depth. That's the effective That's the effective radius, but it's flowing out here. So if you take the total area and then subtract the area of this, the inner core, then you get the area the current's flowing through. It's flowing through this area. Do you follow me? So that means down here, you're going to have, well, the area of the wire is pi a squared. Do you agree with that? And then you're going to subtract off that inner core, which is be minus pi, and then it would be A minus the skin depth squared. And I'm just putting down what the different areas are. Can everybody see this, guys? Y'all understand what's going on here? All right, so that's the real formula for AC high frequency. Now, what it most of the time comes down to, if the actual skin depth is much, much less than A, say by a factor of 5, then you can say that the actual RD or RAC, the high frequency, is equal to the length of the wire over sigma. But now what you can do is this. You can say this thing looks like a very thin strip, so you can just cut it and lay it out like this. And then the length of this would be, the perimeter would be 2 pi A, and the thickness would be delta. And what you'll find out that comes out to be simply 2 pi A times the skin depth. That'll be the new effective area. And that's RAC if that condition is met. Are you with me, class? These are straightforward calculations. We've actually done this before. Do you all recall?
RAC is RHF, right?
It's R high frequency. They're both the same. And I mean, when I teach the EMC course, it's R high frequency. I think in Wentworth's book, it's RAC. The key thing is knowing when you get there. It's when the skin depth is less than A. All right, now, that's so much as resistance. You've had that. The next thing you have to worry about with a wire is internal inductance. When you're modeling anything at high frequency, inductance becomes a nuisance. You would like zero inductance, but you can't have that. And I can speak from personal experience. I've had more trouble getting rid of inductance than any other thing when it comes to high frequency engineering. It is an absolute pain in the butt because the only way to get rid of it is make your leads of zero length, and you can't do that. So you have to work around it as best you can. Anyway, now we talk about the inductance, and this is going to be the DC inductance. But write this down. This is internal. What I mean by that, this has to do with the energy stored inside the wire, not outside. Only inside the wire. So when we talk about DC inductance, first when we draw a wire again is going to have length L. It's going to have a radius A. And it's going to have an area A equals pi A squared. Same as before. And LDC will be equal to the DC inductance per unit meter. I don't know if you remember this. It's just mu over 8 pi. And that's henries per meter. How many remember that this inductance doesn't matter on the radius of that wire? Does anybody remember this at all? You do? Good. this is one of the interesting things about internal inductance. Regardless of the radius of the wire, it remains the same. Unlike resistance, here, internal inductance doesn't matter. It is proportional to the length, though, and that makes sense. The longer something is, the more magnetic energy there is, so you need to include that. That's DC. Now, LAC, this is a little more complicated equation. Y'all realize that resistance was simple. It was length over sigma and times the cross-sectional, divided by the cross-sectional area currents penetrate. With inductance, you have to calculate the magnetic field, and then you have to calculate the magnetic energy density and integrate it in that area to get and set it equal to 1/2 Li squared. And it's more and more calculations, and I'm already out of time here. But LAC is this, just write this down. It's equal to 2, all right, times LDC, that's up here, all right. Then it's times, and then it's going to be equal to the skin depth over the radius. And you can look that up in your book. Whitworth may not have that, but this is the way I like to remember it. You take the DC inductance for a given length, multiply it by 2, then multiply it by the ratio of skin depth over A. And you can look that up. And you can see when the limit of skin depth goes to 0, it goes to 0 as well. There is no internal inductance. There is no internal energy when there's no skin depth. That should make sense. I'm out of time. Yeah?
Search was Friday.
Yeah. It's on radar. And anything else in the last 5 weeks of lectures, whatever?